Right, class. So maybe let's discuss this example. So first, you're given a graph. So the first step that we're going to do is to construct the adjacency list. Okay, so let's say we're going to keep track of this. So these are the vertices. 2 has no neighbor. 3 has 2 neighbors, 8 and 10. 5 has 1, 11. 7 has 2, 8 and 11. 8 has 1, which is 9. 9 has none. 10 has none. 11 has 3, which are 2, 9 and 10. Okay, let me double check. So I have 8 vertices, 1, 2, 3, 4, 5, 6, 7, 8. And the number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9. Alright. Okay, so now let's suppose this is the adjacency list. Now, some of you may come up with different adjacency lists than this one. So as far as the graph is concerned, the information is the connections. It's not the ordering among the vertices, right? So that means that you may have a different way of representing adjacency list, but as long as you have all the vertices, you have all the edges, it's still a valid answer. Now, if this is a graph, then we are going to do topological sorting. And the way we're going to do that is by, first of all, creating a stack. And this stack is going to contain the final topological ordering that we are going to return. So then we are going to start the DFS. Now, once you have an adjacency list, the way that the code would actually work is always to start from the first thing that is on your list, which in this case is 2, because 2 is first in the list. Now, if you have something else that is the first part of the list, then you could have a different order. Now, so first we're going to start DFS from 2. But from 2, there is no neighbor. So essentially DFS ends immediately. Upon return, it will go into the stack. So then 2 will make up the first thing that goes into the stack. Now at this point of time, we have visited 2. But we haven't visited anything else. So we go on to the next part of the list, which is 3. So we start another DFS all over again. So 3 will go on to 8. 8 will go on to 9. 9 has no neighbor, so 9 returns. 9 returns. Upon return, 9 goes to the stack. Then we have 8. 8 will return to 3, right? So upon return, 8 goes to the stack. 3 still has another neighbor, 10. So then it's going to go on to 10. But 10 has no neighbor, so 10 will return. Upon return, 10 goes to the stack. So by now, 3 is done. So upon return, 3 also goes into the stack. So now you have done 2 DFS. One starting from 2, another one starting from 3, right? So 3 is already visited. So are 8, 9, and 10, right? Now we go on to the next one that is unvisited, which is 5. So we start another DFS. 5. 5 will go on to 11. 11 will go on to 2, but 2 is already visited. It will go on to 9, 9 already visited. It will go on to 10, 10 already visited. So then 11 will return. Upon return, 11 goes to the stack. Then 11 returns to 5, nothing else there. So then 5 goes to the stack. Now at this point of time, 5 and 11 are also done. So, but your stack is not complete yet because there is still one more vertex that we haven't covered yet, and that is 7. So then we're going to start another DFS all over again. So starting from 7. But from 7, there are only 2 neighbors at 11 and they are both already visited. So then we will end immediately and 7 will go to the stack. Now at this point of time, everything has been visited and you get a sequence of vertices in the stack. And we can check that they are topological ordering by first making sure that all the vertices are there, and second, all the edges are going to be pointing forward. So then we just check whether the edges are pointing forward. So if we reproduce all the edges here, so 2 has no neighbor, 3 goes to 8 and 10. So 3 goes to 8, 3 goes to 10. 5 goes to 11, that is still pointing forward. 7 to 8 and 11. So 7 to 11, 7 to 8, 8 to 9, 9 to nowhere, 10 to nowhere, 11 to 2, to 9, to 10. So all the edges here are pointing forward. So which means that you get a valid topological ordering. Right? Now, you may have a different answer as long as you got all the vertices, all the edges are pointing forward, then it is still a valid topological ordering. Okay? Now, here we would like to emphasize for clarity, DFS and topological sorting are two different things. So DFS is just a way for us to traverse the graph. Topological sorting is a specific algorithm that makes use of DFS to achieve a particular purpose, which is to sort the graph. Right? So in some sense, the analogy is like saying that insertion sort uses the for loop, right? The for loop is a traversal, insertion sort is the algorithm. So in this case, topological sorting is making use of DFS as a kind of a for loop to visit the different nodes in the graph. But since DFS doesn't guarantee that you're going to visit every vertex, so then topological sorting is going to make use that we are going to try one DFS after another until all the vertices are visited. Okay? Now, any questions up to now? All right. So there are just a few more things about a graph that I would like to mention. One is the concept of the weight of edges. So far we've been talking about edges as if they are binary things. Either they exist or they don't exist. Sometimes you can do weighted edges, which means that you assign a weight to the edges. And the weight has some meaning in terms of, let's say, some cost that you're trying to minimize or some value that you're trying to maximize. Now, this is an example of a weighted graph. So as far as a graph is concerned, it's still similar. You can still represent it using adjacency list. You can still represent it using adjacency matrix. The only difference is that now you have weights, which tend to be some real value that has some meaning in addition to the connectivity. Some of the problems that might be relevant where you have this notion of a weight is called the shortest path problem. I leave it to you as your own research, like what this shortest path problem is. But in a nutshell, it's an algorithm that tries to find out what is the shortest path to go from one vertex to another using the BFS, the breadth first search. So the algorithm is going to base it on the BFS to reconstruct the different pathways that you can go through in order to find the shortest one. It's not by itself within the scope of the course. So this is an example of the routing problem. Now, so in summary, for the graph, right, what are the things that you need to understand? So first, you need to understand the notion of a graph, whether it's undirected or directed, the components, the vertices, and the weights, the edges. Then you have the traversals, different ways to traverse a graph, which has primarily two possibilities, DFS for depth first search, and BFS, which is for breadth first search. And then there is an algorithm, that's an example of making use of DFS to solve a problem that is based on dependency. Now, I'm not sure how many of you are actually pursuing the AI courses, but the AI instructors are basically telling us that it is useful for students to know this notion of graph as well as the traversals like DFS and BFS because it's going to be used extensively in terms of solving some search problems. Because in AI courses, when they look at optimization problems, they look at the different branches that you can go to as a form of a graph. and then they try to optimize certain outcomes, and that usually requires a systematic way of traversing through the graph. So do try to pay attention and try to get your head around this notion of graph ideas and graph problems. Right? Now that's all that we want to talk about the graph.